So let's get started. So let me continue from the point where we stopped last time. So look at this note. There are some situations where when you're plugging the values for the limit, you will find the answer which is undefined. Okay, so for example, look at this problem. When you try to plug in 1 for x, you will get the limit value as if x is 1, you will get 1 cubed minus 1 over 1 minus 1. So this will give you 0 over 0. So this is undefined. So you don't find any answer, right? So in this case, you have to, use some technique to find a real number. Okay, so you could use either factoring technique, or you could use division method or division algorithm to simplify the given problem and try to get rid of this kind of situation. So I will work through problem number 1, for instance. So the question is finding limit x goes to 1 of the function x cubed minus 1 over x minus 1. Okay, so what I'm trying to do is I'm going to factor the numerator. Remember, factoring in college algebra, you could factor this guy. This is in a cube minus b cube form. So 1 could be written as 1 cube. So this could be factored as like x minus 1. Then first term squared. So if you see minus here, you have to write here plus. Then you have to multiply these two terms, 1 and x, which is x. Then the last term squared. Okay, so this is the factor version of x cubed minus 1. Okay. Okay, so that means I'm going to rewrite this as limit x goes to 1 of the numerator can be factor version is this, and you need to divide this by x minus 1. Then you could cancel these two. Now you could plug 1 to the remaining function. Now you are good. You get one real number, right? When x goes to 1, you will get 1 plus 1 plus 1, which is 2. So the limit answer of the problem is 3. So you have to use like these techniques. Now here I'm giving a hint. So factor numerator and check like earlier we did. Now next, the squeeze theorem. Squeeze theorem says that suppose if your function fx is bounded by two other functions hx and gx, okay, if both the function hx and gx goes to L and x goes to C, then of course the middle function fx also should approach to that value L. So that is called the squeeze theorem. If the both ends go to the same point, then of course the middle function also will go to the same point. Okay, so now there are two special relationship or the results we have for the trigonometric functions. So you could use like a theorem. When limit x goes to 0 of the function sin x over x, always going to be 1, and the limit x goes to 0 of the function 1 minus cosine x over x is always x. So use these two results to evaluate the following limit problems. I will work a couple of problems from here. You could try the remaining. Okay. The first one, anyway, the given problem is in tangent x, but the properties we have for sine and cosine. So for that reason, I'm going to change tangent x to, you all know, tangent x is given by sine x over cosine x, right? So instead of tangent x, I'm writing sine x over cosine x. Okay, but anyway, there's x in the denominator, so I'm writing that x also. So now this could be written as limit x goes to 0. So you could separate these two guys together times, so you could write 1 over cosine x separately. Okay, so we have the limit properties. If you have two product fractions, you could split them into two limits. So this is going to be limit x goes to 0 of sine x over x times limit x goes to 0 of 1 over cosine x. By using the properties here, property number 1 says limit x goes to 0 of sine over x is 1. So it's all going to be 1 then. When x goes to 0, you will get here 1 over cosine 0, right? So this is going to be 1 times 1 over cosine 0. Remember, cosine 0 is 1, therefore answer is 1. Okay, cosine 0 is 1. That is there. So you have to think about the second and the third one. And the fourth one, you could use the property, second property, right? 1 minus cosine x over x limit x goes to 0 is 0. So if you want to use that, you have to rearrange this, the given expression. I'm going to rearrange this. This is going to be limit x goes to 0. Okay, so I could rewrite this as, remember, I'm going to bring 1 minus cosine x somewhere here. So this could be written as, let us separate cosine x and 1. And I'm writing sine x. This. Again, you could split these two into like this. Okay. So this is nothing but using, separating two fractions, right? Using the expressions that given. Now you could split, the limit to these two fractions separately using the limit properties. Okay. So if you want to, reform, you could just keep on doing. And I have to create here 1 minus x, right? So for that reason, I am pulling negative sign over 1/2 outside. So you will get 1 minus cosine x, because I need to bring 1 minus cosine x anyhow in the numerator. So I am putting negative sign outside of this expression. And you see x down minus here. I'm putting half outside of the limit. So I'm writing like this for the second piece of expression. Now, by using property number 1 and 2, we say that this is going to be negative half pulling out, and the limit x goes to 0 of 1 minus cosine x over x. Then this is negative half of limit x goes to 0 of sine x over x, right? Now, using those properties, you could say that these are going to 1. 1 minus cosine x over x goes to 0 by using property number 2. So this is going to be 0 over this one. By using property number 1, it says sine x over x, x goes to 0 is 1. So this is going to be 1. Therefore, answer is negative half times 0 minus half times 1, which is just negative 1/2, right? That is the limit of this trigonometric expression. Okay, so you have to somehow bring sin x over x and 1 minus cosine x over x by using some algebraic techniques you learned. Okay, that is there. So please work on the remaining problems here I'm leaving. So you could try those problems, and later this week I will upload the solutions or the completed notes into Georgia View. Okay. So how about 1.4? This is about talking about the continuity of a function and one-sided limits. Okay. Now let's look at the first definition here. The function f is continuous at given point C when these three conditions meet. Okay, so the function is continuous at C means these three should be satisfied. Okay, so the first condition says that function is continuous at C means, first of all, function should be defined. Defined means function should have a good value, real value at that point. Okay, the function should be defined at C. The second condition is there should be a limit for the function. Limit should be there. Okay, so that is the second condition. The third one, the limit answer you got in second part and the function value in the first part should be equal with each other. Okay, so these are the three conditions you have to keep in mind. Okay, the function is continuous at C, that means function should be defined at C. The limit should exist at C, so the limit value and the function value should be equal. Okay, then you could say that function is continuous at the point C. Okay, the definition. The function is continuous on an open interval AB when the function is continuous at each point in the interval. Okay, the function is continuous on the entire real number, then we say that function is continuous everywhere. Okay, if one of these conditions is not satisfied, then function is discontinuous at that point. So there are two kind of discontinuous available. One is one is removable discontinuity, and the one is non-removable discontinuity. So the first removable discontinuity will be like this: function is very good except at one point in the interval. Okay, you see there's a hole here, so function is not continuous at that point. Even though there's a limit, right? Function is not defined at C. So if you see like this case, except at one point, function is very smooth and continuous, right? So then you could call these kind of functions as removable discontinuity. But if there is any jump or big gap between two ends, then we call function is discontinuity with non-removable case. Okay, these are the two cases we have to keep in mind. So the first one, the removable discontinuity is somehow okay because you could make the function continuous by redefining function value. Okay, but for the non-removable, you cannot do that. Okay. Okay, so discuss the continuity of the following functions. What kind of continuity these functions has? Okay, so you could work on last two problems. I'm going to do it now. So the first one, so just I'm outlining, the work here, but later I will upload the complete work. So the outline for the number one is it's very clear that function at 0 is undefined because you will get this value. This is undefined. Okay, so I see the undefined point. Therefore, among those three conditions, equal to look at the first condition. Function is If it is continuous, function should be defined, right, at 0, but this function is not defined at 0, therefore function is undefined at 0, therefore function is not continuous at 0, not continuous at 0. Okay. So for the second one, think about that. For the second one, again, function is not defined at -1 because you see if x is -1, the denominator getting 0. Okay, so f of -1 is undefined, it is 0/0. So again, function is not continuous. F is not continuous at -1. Okay, so you could think about the third one. The cosine function, remember you learned, cosine function is very good function. It is continuous everywhere. Okay, so if you try to graph the cosine function will be very smooth curve. It will go all the way, continuous everywhere. Okay, there's no discontinuity point. Therefore, this function cosine x is a continuous function. Okay, the real line. So now, what kind of discontinuity you have for number 1 and number 2? Okay, so remember, limit x goes to 0 of the function here is nothing but limit x goes to 0 of 2 over x. If the limit times are also going to be infinity, then that function is, if the limit times are also infinity, then that function is going to be non-removable. If you find good number for the limit, then that function is going to be removable discontinuity at that point. Okay. So now look at here. The limit x goes to -1 of the function fx. If you try to find this limit, try to find the limit of this function. Remember, you could simplify or you could factor the numerator now. So numerator will be x minus 1 times x plus 1, difference of squares, factoring, and this is x plus 1, and you could cancel x plus 1, yes. So we get good number of limit. So if we get good number for the limit, that means function is always going to be the removable discontinuity. If it is not good answer, if you get infinity answer for the limit, that function is not removable. Okay, now this function is removable. Discontinuity. It has removable discontinuity at x is -1. Okay, but the last one is continuous everywhere. Okay, there. But this is one-sided limit. So if you see plus or minus sign on the superscript, then we call this as one-sided limit. Okay, so we use like this notation. That means x approaches c, okay, from the right side. If you see some number negative sign, then x approaches to that value c from the left. That's the meaning. Minus left plus right. Okay, so that is given in the picture. So you see for limit c goes to plus c plus x goes to c plus of the function. That means from the right side x approach to c, the function value is L. Therefore, that is given by limit x goes to c plus, the function is approaching to L. The limit from left means what? X approaches C, x approaches to C from the left. Okay, but again, function value is L at that point C. Therefore, it is written as limit x goes to C minus of fx is L. So here we consider only one side at a time, right? Maybe either right or left. So which is called the one-sided limit. Okay, but remember, no confusion. So if you see like this, just limit x goes to C of some function, this means you have to consider both the sides. If you don't see any sign here plus or minus, always you have to consider both the sides. Okay. Now there's a theorem, existence of limit. Let it be a function and let C and L be real numbers. The limit of the function fx when x goes to C is L if and only if left side limit and right side limit is L. Okay, so limit x goes to C of fx. If you are given this guy say L, this means this is true if and only if limit approaching from the left of the function should be always equals to limit x goes to C from the right of the function. But these two answers are also supposed to be L. Then only you could say that function having limit value at C when x goes to C fx, which is L. So this is called the existence of limit. Okay. So definition of continuity on the closed interval. A function is continuous on the closed interval AB. That means function should be continuous in the open interval plus these two conditions, are supposed to be held. Okay, so we are given an interval. Say this is a real line. Say this is A and B. Okay, if the function is continuous in closed interval, remember closed interval means you are including the endpoints. So endpoints are included. That is called the closed interval. So for the closed interval, we use bracket. To denote the closed interval, we use the bracket. So the meaning is all the real values in between A and B, and also A and B are included. Okay, so endpoint. So endpoints are included. But for the open interval, suppose if you see two numbers from A to B, so we use parentheses for open interval. So that means everything is included inside the A and B. A and B are not included in our domain. Okay, that's called the open interval. We all know study, right? So endpoints are not included here. So endpoints are not included. Okay. So if the function is continuous on the closed interval, that means it should be continuous on the open interval, and the left limit of B should be defined, which is f of B, and also right limit of the function at A should be again defined, but that value should be f of A. So this condition should satisfied for being continuous on the closed interval AB. Okay, look at this picture. Function is continuous. We all know the meaning of continuous. The function is, smooth function everywhere. So inside the A and B. So you see here. So this is the given closed interval. Function is very good, continuous, and the endpoint also defined. So function is continuous on closed interval AB. Okay. So now, so why don't you think about these two? So think about these two. I will upload the work couple of days, but I just want you to try. Okay, you have to try. So simply just think about how these functions are, defined, and in which interval it is having, discontinuity property or continuous property. So simply just explain them. Okay. So there are some properties of continuity functions. If function f and g are continuous at particular point C, then these are true. The function b times f also continuous. So if you add two continuous or subtract two continuous functions, the resultant function also going to be a continuous function. If you multiply two continuous functions, then the product function also going to be a continuous function. And if you divide one continuous function by another continuous function, provided the denominator is not equals to 0, then again f over g function also going to be continuous function. Okay, this also is also continuous at that particular point. C. This is all continuous property. Okay, so there are some special functions. The polynomial functions are always continuous throughout the real line, everywhere continuous. Okay, polynomial function. The rational function px over qx also continuous except at those points, the denominator getting 0 point. Other than that, function is continuous. Okay. So the radical function also going to be continuous on its domain, and the trigonometric functions, sine, cosine, tangent, cotangent, secant, and cosecant, these all functions are continuous on its domain. Okay, on its domain. That is there. So now, next property, if you have two continuous function f and g, okay, function g is continuous at one point C, and function f is continuous at gc, then the composite function f of g is always continuous at C. Okay, so you could combine two continuous function, then the resultant function, composite function, also going to be continuous. Okay, so I have explained here those things, and we could try to work with this problem and check the answers here. So if you have any questions, please email me, then I could explain. Okay. So there's another theorem we call the intermediate value theorem. Intermediate value theorem says if f is continuous on the closed interval AB, where f of A is not equals to f of B, function value at A is not equals to function value at B. And if you have a real number k between f of A and f of B, then definitely there's a point you will find in the in the closed interval AB where function value at that point give you k. Okay, so that is explained here. this picture, intermediate value theorem. Okay, so you see this function is continuous, and if you find the 2 points which are not equal, definitely you will find in between point, between A and B. So in that point where your function will be defined, and that function value is nothing but k. Always it is possible for you to find one k between f of A and f of B, such that f of C is equals to k. Okay, so this is called the intermediate value theorem. So always you could find one point on the domain such that f of function value at C is equals to that k. Okay, clear? Okay, so even though if you have this theorem, so the converse is not true. Okay, that's what it says. So continuity will give you an intermediate value, but the converse is not true. Intermediate value always will not give you a continuous function. Okay, that's what it is here. Even though you could find one point where the function having defined at that value, but function not necessarily having that continuity property. So it is not true. Okay, only one way is true, another way is not true always. Okay, that is here explained in this picture. It is there. So again, you could think about 1 and 2. So I'm going to post the answers for 1 later. So number 2 already worked here, so you could go through these steps and make sure that you understand and watch the videos from the sections. Okay. Okay, so this is about finding limits. Okay, finding limits, but this is infinite limits. Your answer is now going to be infinity. Okay, so if you are given a function, the open interval function is very good, defined everywhere except at one point C. Okay, if at that point limit is infinity, then we call function has infinity limits at C. Only one point is not good, right? Function is undefined. Other than that, function is very good, except at that point. And if you see like this scenario, we say that function has infinite limits. Could be negative infinity or could be positive infinity. Okay. So you, for example, look at this problem. So what can you say about the limit of this problem? Limit x goes to -2 of -4 over x plus 2 function. Okay, so if you simply look at the function, if you try to plug in -2 for x, you will get 0 in the denominator. Okay, so if you try to plug in -2 here, this seems you will get the answer -4 over 0. So we all know any number over 0 is going to be infinity, right? So this is nothing but negative infinity. Okay, your question is now, will it be function good except h2? So could you find an open interval which contains that point -2, where function is very good except h2? So everything is explained here. If you look at the graph of the function, if you try to graph this function, okay, so look at this problem. So if you look at left and right limit of this function, Okay, so if you look at left and right limit, so near -2, the limit approaches positive infinity from one side and negative infinity from the another side. So you have two different answers for both the ends. So you can't have two different answers in left and right, right? If you want to have a limit answer, remember always left limit should be equals to right limit. Okay, so look at this statement. So why don't you graph this function? This is your work. Graph this function and check. Okay, graph this function and check. So when you find the limit when x goes to -2 from the right, you should get the answer negative infinity. But the limit x goes to -2 from the left will give you, positive infinity. So right limit is negative, left limit is positive. You get two different answers, right? So if you have left and right different answer, that means limit does not exist, right? If limit exists, you have to have same answer. Remember we had last time. So this reason there's no limit at -2. Okay, that's why limit does not exist. Okay, at -2. Okay, so understand that point. Now the definition of the vertical asymptote. Fx approaching infinity or negative infinity could be as x approaches to some point C, maybe left or right, then we say that x is equal C line is a vertical asymptote. Okay, so when if the function approaches infinity, then we call function has asymptote at that particular x value, vertical asymptote. Okay. So I think you have studied about vertical asymptotes in college algebra or in pre-cal. So please go through those things one more time to get better understanding about vertical asymptotes. Okay, so look at this example. You are given simple function 1 over 2 times x plus 1. If you try to graph this function, you will get exactly here. So remember, at -1, function is approaching to the positive infinity from the right side and the negative infinity from the left side. Okay, so function is having infinity value at that point. Therefore, function has a vertical asymptote at x is equal -1. Okay, remember vertical asymptote is nothing but a straight line, vertical straight line. You see the dot line? This is called now vertical asymptote, which is x is equal -1. So the equation of this line, dotted line, is going to be x is equal -1. So if you are asked to find the vertical line, simply find the vertical line equation at that point. Okay, that is there. Look at the second example. Suppose if you are given this function, h function. Okay, so you could factorize the denominator. So you will get x minus 1 times x plus 1. Now you see the denominator will get 0, right? When x goes to 1 and x goes to -1. Therefore, you find now two vertical lines, vertical asymptotes. So you can see that the denominator is 0 when x is -1 and x is 1. Therefore, you find now two vertical asymptotes. Okay, -1 and the +1. Always, if you graph the function, you will get better understanding. For tangent function also having the vertical asymptotes like this. Again, like normal limit problem we studied in 1.2 and 3, here also we have some properties for infinite limits also. If the function having infinite limits, then the sum of the function or difference of the function is going to be again infinite. And if you multiply one infinite limit function with another function, always you will get infinite function. Okay, maybe positive, maybe negative. So if you divide one function by another, so if you see the denominator function is infinite function, then let's see, then it's going to be again 0. So these are basic properties you could memorize. Okay, you could memorize these.
Could you possibly work out a couple of problems from the homework on 1.4?
Yeah, that's what I'm looking. So you are asking from web design, right?
Sir?
Is that from web design you are asking?
Yes, sir, on section 1.4. It's number 5 and 12.
You mean this one, finding limit?
Yes, sir.
Okay, so what you want to do is here, find the limit if it is exists. Answer is that's not exist here, right here. Okay, so what will happen if you try to plug in? Would you simplify that? So is that possible to simplify this numerator? Let us simplify this. So question is finding the limit delta x goes to 0 from the right of 5 over x plus delta x subtract 5 over x over delta x. So now the thing is you need to simplify this numerator and use some algebra and simplify the numerator part. So remember, if you want to add two fractions, I'm doing the sketch work somewhere here. Okay. So I'm trying to simplify x plus delta x. So this is delta x, just a number, just like a variable or number. You could think about this just to be like a number. So now, how do you combine these two fractions? Remember, you need to have common denominator, right? So here I see x plus delta x, here I see x. So I'm going to multiply here by x and here also by x. But here I'm going to multiply with x plus delta x. And here I'm going to multiply x plus delta x. My idea is to make x times x plus delta x in the denominator to make equal. So this will give you 5x over x times x plus delta x in the denominator. Here you will get 5x plus delta x over x times x plus delta x, right? Remember, when you subtract or add the two fractions, if you see the common denominator, you could simply directly subtract these two. So I'm going to subtract. In another word, I'm combining under one fraction. That's why I'm doing this. You see now, you could write as one fraction. Now distribute negative 5 inside and we simplify it. Minus into plus, minus 5 times delta x. Okay. So now we could cancel this guy. You will get simply negative 5 delta x in the numerator over x times x plus delta x in the denominator. So I'm going back here and I'm plugging those answers I got. Negative 5 delta x. I'm writing an answer for the numerator, okay, for this part. I started from there and I worked and I got this answer. Negative 5 delta x over x times x plus delta x. So this is the one I am getting only by simplifying the numerator. Remember, in the denominator itself, you see the delta x. So it should be somewhere here. In the denominator, there's delta x. Now you see in the numerator also, I see the delta x. These two going to be cancelled with each other. So it's now going to be limit delta x goes to 0 plus of negative 5 over x of x plus delta x. Okay, remember the meaning of this is delta x approaching to 0 from the right. Okay, so this number, if you locate in the real line, 0 is somewhere here. Delta x approaching to 0 from the right. So this is nothing but very small number close to 0. You could think of like 0.0005. But it is in positive direction, so it's kind of positive 0.0005. Very close to 0, right? But positive number. What will happen if you plug in some very small number instead of delta x? That number also going to be very small, right? Very close to 0. So that means your answer is going to be negative 5 over x times x, which is x squared. So this is going to be the limiting answer of that problem. So, now the question is here, find all the values c such that function is continuous everywhere, right? Negative infinity to positive infinity. Remember, this is nothing but step function. So you are given a step function here. So the idea is now, okay, let me copy down this problem also. I need to show you the work. Okay, so let me do here somewhere. Again, we are doing 1.4, problem number 12. Okay, so the question is, you need to find all possible c, okay, such that the function f should be continuous everywhere. Negative infinity to positive infinity means whole real line, no? Remember, the given function is now a step function, means function has two different values, right? Function will have 4 minus x squared if x is less than or equals to c. Other than that, function is simply x when x bigger than c. Okay. Remember, in order to have function continuous, only the problematic point is now c, right? Only this point now is a problematic because at that value, function having two different values. Okay, remember, to be a continuous function, there are three conditions always should satisfy. Function should, so you recall, okay, recall the continuity functions properties. If function is continuous at a, I'm using that point as now c. If the function is continuous at c, there are three conditions should satisfy. Function at that point c should be defined. The second one is the limit of the function, limit x goes to that point. This also, should be there, right? This answer should exist. And the third condition is what? The limit answer should be equals to the function value. These are the three conditions supposed to be there, okay? Now the thing is, we are telling that you need to find all possible c real values such that function is continuous, okay? That means, remember here, what's the meaning of this? The meaning of this is you are plugging all possible x which is less than or equal c, okay? Suppose if this is a real line, c could be any real number here, right? So now x is less than or equal c means you are plugging all possible x values in this region, including c, okay? But for the second case, you are plugging all the x values which are bigger than c, that is this side. If the function is continuous at c, remember function should be defined at c, and also limit from the left should be equals to limit from the right. Okay, so keep in mind that point. So I'm going to find the function value for both the cases. Function should be defined at c, right? Okay, so what you want to do is you simply plugging the function value at c. So the first function, the first possible function at c will give you 4 minus c squared, right? Simply plugging c here. This should be equals to the function value here as well. Okay, so what I'm trying to say is you have to equate those two possible functions by plugging that particular value c to x. In this way, you are doing what? You are simply applying this condition, right? Limit from the left should be equals to limit from the right. That's what you are doing here. So now your task is to solve this equation for c. That's it. They are asking you to find all possible c values, right? So how do you solve for c? This is a quadratic function with unknown c. So you have to move all the coefficients one side, all the variables one side, okay? So I am rewriting this. I am moving c to the left and keeping right side as 0. So I'm rearranging this. This is negative c squared, negative c plus 4 equals 0. Okay. Now multiply everywhere by negative. I'm making here positive. So you get c squared plus c minus 4 equals 0. Now you need to solve. This quadratic equation. Do you know how to solve quadratic equation? So you have to solve for c using b squared minus 4ac.
Mm-hmm.
So this is a quadratic equation, right? So you might have c like this. Instead of c, you might have seen with x. How do you solve this equation? Using b squared minus 4ac, remember?
So it'd be c plus 4 times c minus 1 equals 0.
Hold on.
Never mind.
This is the formula now we are going to use, okay? You know, a, b, c are the coefficient of the quadratic function. So in this function, a is the coefficient of x squared, which is 1. B is the coefficient of x, which is also 1. And c is nothing but the negative 4. Okay, so now your task is to plugging those values here. So negative b is 1 plus or minus square root 1 squared minus 4. A is 1 and c is negative 4. It's all over 2. A is 1. So could you simplify further? Negative 1 plus or minus. Inside the radical, you will get minus into minus plus 16. 16 plus 1 is 17. I'm getting weird number. I don't know. Okay. So now you know for x answer, we have two answers. If you take positive sign here, plus sign, you will get one possible x answer, which is negative 1 plus square root 17. Do not round up. Write the exact answer like this. Then if you take the minus sign, then you will get x answer as negative 1 plus, sorry, this should be minus. This minus. Okay. Now we know square root 17 is very close to 4, right? 4 squared is 16. So this is positive number. This is going to be the large number. This is going to be a small number. So these are the two possible values for this quadratic x squared plus x minus 4. I simply switch c to x. Okay. Nothing is wrong with that. Okay. So you could change the variable. We are solving for c means you are solving for x. So these are the two possible answers. Okay, so you have to type this answer and let's see whether this is now coming correctly. So could you type this? -1 plus square root 17 over 2. This is the largest, and the smallest going to be -1 negative square root 10 over 2. Should we understand now?
Yes, sir.
Yeah. So we are basically using that continuity property, okay? So you simply plugging those two, values for the function, different functions, simply plugging those and solve for x. Okay, that's to maintain the continuity, no? So you have to have same function value at the both ends. That's what I'm doing. So I'm going to upload all the completed work for this section. Did I upload all the work in Georgia View?
Sir?
Did I upload all the completed notes in Georgia View?
I saw where you uploaded them.
Yes, so answer is there, so you could check with my work and with your work, and let me know if there's any question, okay?
Okay, the quiz is due tomorrow night, right?
From Georgia View, right?
Yes, sir.
Yes.
And the test will open Sunday at 12.
Exactly. I'm going to send you one more notice before the test. So maybe on Friday you will see one more announcement about test, okay?
Okay, and you'll
Hold
upload
on.
the
You
practice.
have the practice test, right, already?
Yes, sir. We just don't have the answers to them yet.
I'm going to upload just now, okay?
Okay.